Hello and welcome to the second video in our fifth class time series of lecture videos. We'll be looking at now the reactivity of benzene and discussing a bit of its observed stability, and we might even go into reasons why, at least touch the surface of that. Benzene is remarkably stable. Most drugs contain aromatic rings, and stable, by stable I mean less reactive, so lower in energy. Of course, we have several chapters on reactions that we can do with aromatic rings, so it doesn't mean that we cannot do reactions with these aromatic ring systems. It just means they are less reactive than, say, linear trienes, which we saw, readily undergo, electrocyclic reactions under thermal and photochemical conditions. For example, if we expose benzene to bromine, whereas bromine might react with an alkene or do other radical reactions, there's no reaction unless we have some sort of catalyst present. Again, if we try to hydrogenate these double bonds by, putting benzene in with hydrogen gas and platinum or palladium, there is no reaction without high temperatures or very high pressures. Typically, those reactions used to be carried out in things called bombs, so sealed metal containers, and occasionally those bombs would go off. But now we have new technology where we can achieve high temperatures and pressures in a flow system. So there's, a small steel pipe and very, very small diameter, think wire size, that we flow a solvent through with benzene, and we can achieve high temperatures and pressures in the catalytic cartridge of that system, and then we don't have to worry about, taking walls out at the university unintentionally. Let's consider the change in enthalpy of hydrogenation for cyclohexene and 1,3-cyclohexadiene, for instance. Here we've got cyclohexene, we add hydrogen gas, catalytic platinum or palladium, we generate cyclohexane. What's our change in enthalpy? Well, we release 28.6 kcals per mole. How about hydrogenating cyclohexadiene in a 1,3 conjugated pattern? So we use two equivalents of hydrogen gas, another platinum catalyst. We reach the same cyclohexane, but we only get 54.9 kcals per mole out, as opposed to what? Well, we might have thought that, well, geez, since we're hydrogenating two double bonds, we should get twice this amount of energy out for the hydrogenation of cyclohexene. And to show you what I'm thinking of mathematically, here we go, right? We might expect a change in enthalpy of 2 times negative 28.6 kcals per mole, and that would be negative 57.2 kcals per mole. However, by experiment, we only observed 1,3-cyclohexadiene when we hydrogenate it to release 54.9 kcals per mole. Well, what's the difference between our expected hydrogenation enthalpy change and the experimental one? Well, your text characterizes that as a resonance stabilization, which is to say that placing those two double bonds in a conjugated way such that you have this, pi system of electrons, we lower in energy each of these alkene bonds, and we don't get as much energy out when we hydrogenate it. And so that difference in energy is plus 2.3 kcals per mole. Yeah, I guess I can't really call it resonance stabilization because I've said that resonance is a lie, and I have to live with myself and make a consistent story for you. So I'm trying to give you or push you towards the molecular orbital sort of conception of why these pi bonds are low in energy, but that's just me. Anyways, 2.3 kcals per mole, we think, geez, that's a small amount of energy, but it's really quite significant and noticeable, in a statistically significant fashion. It's not like that's within the error of our devices. our measuring devices. So then we might say, okay, a procedure Volhart goes through in his text is, let's try to calculate what the hydrogenation of benzene would give us in terms of a change in enthalpy if we could achieve high enough pressures and temperatures without blowing up walls in the university. So we've got 3 equivalents of hydrogen gas, platinum, we're getting cyclohexane again. And you might speculate that you do some sort of predictive calculation where you take 3 times the change in enthalpy for just cyclohexene, and then you add in 3 times of the resonance correction for cyclohexadiene, the 1,3-cyclohexadiene, right? And I'm not quite sure myself why one would consider this a nice predictive method for this calculation, but this is an exercise Volhart does, and it seems to make sense to him as some sort of predictive exercise. And so here we go, 3 times negative 28.6 plus 3 times plus 2.3 kcals per mole, and we get a prediction of negative 78.9 kcals per mole. But lo and behold, when we actually hydrogenate benzene, we only get 49.3 kcals per mole out in terms of energy and in our change in enthalpy. Wow, that's quite a difference, right? That's quite nearly 30 kcals per mole less than what we calculated, even trying to correct in our crude and naive way for having some sort of resonance stabilization of these 3 double bonds, in a conjugated sense. So here we have sort of a diagram, not drawn to scale, I'm sure, where we've got 28.6 kcals per mole coming out of the hydrogenation of cyclohexene in terms of a change in enthalpy. We're all going down to the same cyclohexane molecular level of energy. Here we've got the 1,3-cyclohexadiene being hydrogenated, and we get negative 54.9 kcals per mole. But when we go to the cyclohexatriene, otherwise known as benzene, and hydrogenate it, we predict, we might get, negative 78.9 kcals per mole out. But in fact, we get less energy out than when we hydrogenate 1,3-cyclohexadiene, right? We only get 49.3 kcals per mole out. And so we could term that a resonance energy stabilization of 29.6 kcals per mole, almost 30 kcals per mole stabilization by putting those 3 double bonds in the 6-membered ring. So there's something quite special about these aromatic rings and their stability. And in fact, one could oxidize 1,3-cyclohexadiene quite easily to benzene, right? By cooking it up with platinum, we would extract 2 hydrogens and we would actually get energy out, right? From negative 54.9 to this level, right? Negative 49.3, that's the difference of a little over, 5 kcals per mole. So that's actually how the reaction would go if we put 1,3-cyclohexadiene with platinum in some solvent or just neat, and we heated it. We'd get hydrogen gas coming out and benzene, which is much more stable by 5 kcals per mole. So of course, we might ask, why is benzene stabilized much more than, maybe a linear hexatriene, right? And if we look at hexatriene using our old Lewis structure view of the world, you could create minor resonance forms where you have charge separation, right? All minor forms have charge separation, and some atoms which have unfilled octets. In benzene, each resonance structure is neutral and has a filled octet, right? We discussed this, and we couldn't identify which of these resonance structures would be major. They're equivalent, right? So 50-50%. weighting to them, and of course we did some sort of hybrid structure to depict that the reality of benzene is not one or the other. It's some hybrid of both resonance forms. Of course, the deeper understanding is the molecular orbital view, which we'll get to perhaps at its most deep level in the 6 class time series of lectures. At any rate, all carbon-carbon bonds in benzene are precisely 1.39 angstroms. So what this indicates is there aren't really alternating double bonds and single bonds, but each bond is equivalent in length and strength. Whereas for, you know, a linear system of alkenes or pi bonds, you do really have a double bond character, right? And a shorter bond length, maybe 1.34 angstroms for a 1,3-butadiene double bond length, and 1.47 angstroms for the single bond length. I think that's about where I want to end this particular video. I will see you in the next one.